Greetings from Raleigh, North Carolina. This presentation involves the diffusion of moisture in southern pine wood. It is part of a research work at NC State University involving Harry Wang, Perry Peralta, Phil Mitchell, and Ilona Peslin. Moisture accumulation in a building envelope with cross-laminated timber as wall component is an important consideration in the adoption of CLT in the construction industry. Water accumulation could cause conditions favorable to decay and mold. In addition, internal stresses in the wood and in the glue line due to moisture content variation could lead to structural failure. Moisture transfer in CLT is highly influenced by wood species. Currently, no diffusion data exists on CLT made from southern pine, the most widely planted tree species group in the US and perhaps in the world. In addition, previous work have shown that the adhesive layer could affect moisture transport in CLT. A study was performed at NC State to quantify moisture transport on the cross-laminated panel itself, to evaluate the effect of the adhesive region on the diffusion rate, and to measure the diffusion coefficient of the wood component. This report details just one aspect of the bigger study, and that is the moisture transport in southern pine wood below the fiber saturation point. The approach for this study involves three stages. First, we performed unsteady-state diffusion experiments. This was followed by steady-state diffusion experiments, and finally, we did some modeling of the diffusion process. For the unsteady-state diffusion experiments, southern pine samples previously equilibrated at 98% relative humidity at 20 degrees Celsius were subjected to one-dimensional drying at 65% relative humidity and 20 degrees Celsius. The slope of the initial linear part of the unsteady-state desorption curve was chosen for calculating the diffusion coefficient. The average diffusion coefficient for the 6 samples was 3.1 times 10 to the minus 6 centimeters squared per second, which agrees well with those of researchers. In the steady-state diffusion experiment, a wood sample was sealed to the lid of a diffusion cup containing liquid water. The cup assembly was then placed in a conditioning chamber maintained at 65% relative humidity at 20 degrees Celsius to establish a moisture content gradient across the thickness of the sample. After staying in the chamber for 60 days, the sample was sliced to determine the moisture content distribution in the thickness direction. On average, a linear moisture content profile along the thickness direction was found. To verify the linear moisture content distribution, simulations were performed on COMSOL multiphysics. The simulations show that in static air, moisture concentration at the specimen inner surface was substantially different from that at the water surface. In addition, the moisture concentration at the specimen inner surface increased with time until equilibrium. After 60 days, a sample in moisture concentration, the change in moisture concentration was negligible at each location, and linear moisture concentration profiles were obtained, indicating that the steady-state condition was achieved within that period. The strong agreement between experimental measurements and simulations validate the measured diffusion coefficient obtained from the unsteady-state experiments. It also confirms the linear moisture content profile from the steady-state experiments. So, the takeaway from the work are that number one, the diffusion coefficient of southern pine was successfully measured, yielding a diffusion coefficient of 3 times 10 to the minus 6 centimeters squared per second. Number two, diffusion modeling allows prediction of moisture distribution in solid southern pine subjected to a moisture content gradient within the hygroscopic range. And thirdly, data from this experiment is a critical input in the next step of the study, which is the characterization of moisture transport in CLT. Before we close, we would like to acknowledge the support provided by the USDA NIFA Integrated Forest Products Research Grant Program under grant number 2012-03699. Thank you for your attention. If you have questions, please contact us at the email address indicated below.